Okay, so I realized that I got cut off on the last video, and I wanted to kind of back up where we were talking about. Again, Newton's laws of motion. First law of motion was the law of inertia. So an object at rest stays at rest. An object in motion stays in motion. And remember that that motion is a constant velocity. So if we're moving along constant velocity, okay, and hence no acceleration, that's Newton's first law of motion. Second law of motion is where we started to look at how we get an object to move is based upon the forces that we apply. Okay, so we apply a force, we get an acceleration. We accelerate our mass. So now we were just talking about the two relationships. So if mass is held constant, the greater the force, the greater the acceleration. If the force is held constant, the greater the mass, the less the acceleration. Okay, so there's relationships between how we look at those, and that all ties into this equation, this F equals ma. And remember, we're talking that this force is a net force. Okay, so we're always going to kind of refer to it as the net force, which really drives back to Newton's first law of motion. An object at rest stays at rest, or an object in motion stays in motion, implies that there is zero net force. Okay, zero net force. We're going to study a lot about this. Which way does the arrows go, and is there a force or is there not a force present in terms of the net? Now, when we start to measure our units associated with force, we look at it in terms of that mass times that acceleration. And when you take a mass, which is measured in kilograms, that's our SI unit, and our acceleration, which is in meters per second squared, we get a kilogram meter per second squared. And then again, if you tried to say that 3 times really fast, okay, kilograms meters per second squared is kilograms meters per second squared, kilograms meters per second squared, it's tough to say, okay? Bottom line, it's just tough to say. So they decided to say, well, let's create a unit, okay, called the Newton that is equivalent to those units, okay? So this is, again, our derived quantity is called a Newton, and it's based on all of those multiples of the fundamentals, okay? So 1 Newton is equivalent to 1 kilogram meter per second squared. This means that when we weigh things, we like to weigh them in newtons. When we find the mass, we're finding the mass in kilograms. We then convert mass into weight. That's going to be kind of that big concept here. Mass does not equal weight. Okay? That was, if there was one thing you remember from 9th grade science, that's hopefully one of those things that you remembered, is that the mass does not equal the weight. The weight is the gravity's effect on a mass, okay? It's gravity's effect on the mass. So in other words, when we calculate weight, we're really taking the mass times an acceleration, but that acceleration is gravity, okay? So you weigh something on this planet because you have gravity. If you stepped on a scale on the moon, you wouldn't have the same weight, okay? Because gravity is different there. So as we change gravity, we change your weight, but your mass remains constant, okay? And that's kind of that fundamental quantity versus a derived quantity. All right, so let's see where we're at here now. When we draw forces, okay, we're going to use arrows because force is a vector quantity. It is a vector quantity. So we typically like to do this thing called a free body diagram or a force diagram or something along that lines to look at net forces. So I may have like an object that is being pulled upward, but it is also has a weight acting down. Well, now if this arrow is bigger than this arrow, there is net force, okay? Because the bigger arrow is obviously bigger than the smaller arrow, and they're acting in opposite directions, which means that they would be opposite each other, so they would take away from each other. Now, if we had a situation where this arrow is equal to this arrow, okay, they're the same size. If they're the same size, that just means that the object could either be at rest or it could be moving with a constant velocity. There's our big picture key things, okay? So if you're not writing this down now, you need to kind of write that down. You may want to pause right now to reflect upon that, okay? All right. Hopefully you're back now after your little bit of a pause. we do start to look at things in terms of a center of gravity. Okay, when I put these little points here, I was looking at maybe an object. So my object might be something like the book that I've got here. Well, this book can be balanced, okay, through its center of gravity. So at some point there is a spot, okay, where all my matter wants to balance. Let's do it this way. There we go. Okay. So you can see I can kind of balance it. It's easier to do, of course, maybe with my marker. Okay. All right. Or maybe my meter stick. Okay. So there you go. I put the center of gravity below my balance point, and that's how I can kind of look at keeping everything in equilibrium. Okay. Equilibrium. What's it mean? Another word for forces are balance, zero net force. Okay. And as I was just talking about earlier, weight is something that we will always call a force. And usually when I write it as the force due to gravity, or it's F of G. Okay, so that's usually what I like to talk about when we talk about weight. You may see that some of our online problems or practice might use W to signify weight. It's fine. It's just notation. It's like you know, how one person calls it, you know, I don't know. It's like just terminology, okay? Syntax, okay? Difference between uses. Okay. So now we should be able to look at our third law of motion. Now, third law of motion is the one that you may remember from 9th grade. This is for every action there is an equal and opposite reaction, okay? Typically we look at this and we say that forces act in pairs, okay? And there has to be two objects acting on it, and so the one force is acted upon by this object, and then the other one is acting upon the other one. So in other words, the bat applies a force on the ball, and the ball applies a force on the bat. And those two forces are equal, okay, in the opposite direction. You have to have two objects, though, when you're looking at this, okay? There has to be two objects. We did this probably in our rocket project, where the rocket applies a force on the Earth, and the Earth applies a force back upon the rocket, okay? So that's where we're looking at it in terms of Newton's third law of motion. So it's now, how do we kind of look at, can we get this forces in contact, okay? So how do we get this interaction between two objects? Typically we have these things called contact interaction, okay? Contact interaction happens between surfaces touching. One is called the normal force, okay? A frictional force, a tensional force, or an applied force, okay? These are the ones that I usually like to see in class. Normal just means that we have a surface and there is a contact force that is always going to be perpendicular to that surface, okay? So if you have two surfaces in contact, the normal force always acts perpendicular to the surfaces that are in contact with each other. That's just how it's defined. Normal forces can be bigger, smaller, kind of depends upon what we need it to be, okay? It's one of these, how big do we need the normal force to be in this situation? Frictional force is kind of the similar thing, and we'll probably get into a lot more details on frictional force and normal forces in a different video as well. Tension force is kind of a tension, so if you're pulling a rope or something, there's usually a tension that's in it, and the nice thing is that the tension throughout a string is going to be the same tension throughout that entire part of the string. It's not like a string can all of a sudden have more tension in one part and less tension in the other part. Okay, it's the same tension throughout the string as long as it's the same string. An applied force is just what it says. It's an applied force. So in other words, it's the force that I am pushing with. Okay, that's what it is. Let's see what else we got. We got our other forces, which are our added distance force. So in other words, there's no contact between them. Gravity is one of these. So we have a gravitational force. So in other words, there's nothing that connects the Earth to the sun, but the Earth and the sun are held together by a gravitational force, okay? It's at a distance. And in fact, if I'm in the air above the planet is actually still pulling on me, and so there is a force that's applied on me. and I apply a force on the planet just in the same sense. So they're at a distance. The other two are electric forces and magnetic forces, and we'll probably discuss those more at a different date as well. So here's our question of the day. So this is the one that you're going to have to come in with now or I'll pass out a slip of paper and you'll have to answer this after you get done watching this video. But an apple has a mass of 425 grams. Okay, what is the weight of the apple in newtons? Now, you can work this problem out. You should be able to figure this out because, again, we know what weight is. Weight is nothing more than a force. Okay, it's the mass times an acceleration. Okay, but be careful because, again, newtons are defined by units, and you have to know what units go into making up a newton. Hint, hint, hint. Okay? So just be careful. You can figure this out. It'll be the question that you'll have to submit on your piece of paper for tomorrow. All right? Signing off. Happy physics.